In this video we're going to determine the concentration or the pH of a buffer made by mixing two different solutions. One is methanoic acid, and we have to determine the concentration of that because it's been diluted. So that's what's happening here. And then we also have to determine the concentration of the ion, that is the methanoate ion, that comes about from the dissociation of sodium methanoate. So sodium methanoate is a salt. Because we know its concentration, we know the concentration of the methanoate ion, and then we determine the concentration of that methanoate ion because it has also been diluted. So there we go, there are the two concentrations of our ions of interest in this buffer. And like all equilibrium problems, we need an equilibrium expression for the dissociation of methanoic acid. So there it is, and there's our methanoate ion as a product of this reaction. So that's really how this buffer calculation is a little bit different. We have an initial concentration of our methanoic acid and of our methanoate ion, and we still have no hydronium ion. We complete the ice table as we have previously, and in this case you'll notice that we have two terms with an X in them. You write an equilibrium expression, Ka, for methanoic acid, and there's the actual Ka value, 1.77 times 10 to the minus 4. We cannot make the assumption on this one because when you divide initial concentration by the K, you get an answer of about 140. So that means we have to go through the long, arduous process of finding a quadratic equation and then solving that quadratic equation. And I'll just remind you, I don't show the full proof, but you do need to be careful when you find your quadratic equation firstly. And secondly, you have to be careful when you're solving using the quadratic formula. These are all possible ways of making simple calculation errors, so you do need to be pretty careful when you go about this process. But if you do it carefully, you will get always two values of x, and you'll always be able to ignore or discard one value of x. In this case, a negative x cannot be plausible because it does represent hydronium ion concentration. So we'll take the positive value, 2.5 times 10 to the minus 4 moles per liter, and from that we simply plug into the pH expression. pH equals negative log hydronium. We get a pH of 3.60, which you were told in the top of the question was the actual answer. Now there's another way to calculate the pH of a buffer. So there are concentrations. We're going to use something known as the Henderson-Hasselbalch equation, and that's given here, and I've given that to you in a set of notes. This makes it a lot easier to find the pH of a buffer. This is only applied when it's a buffer. Now notice the pKa is the negative log of a Ka value. And we know the Ka for methanoic acid, so the pKa is simply the negative log of that value. And then we add it to the log of the anion divided by the acid. Those are initial concentrations in both. And you'll see when we do that correctly, we get 3.60, which not surprisingly, is the same as we achieved when we did it the long method using a completed ice table and everything. So as I said, buffers can be, the pH of buffer can be calculated using this Henderson-Hasselbalch equation. So it is in your best interest to remember that equation.